All right, hello students. Welcome back to another week of chemistry of everyday life. In this week, we will talk about Unit 5, and so we will be discussing nuclear chemistry. And so I want to start off with just briefly touching base on some of the players in their discovery of radioactivity. I won't go into much detail other than to mention their names. You can watch more YouTube videos that has a more historical context. So I want to mention here is Wilhelm Röntgen. He is basically the one who discovered X-rays, and then with his work, Henry Becquerel and Marie Curie mainly are the two people who discovered radiation, that atoms can have this property called radioactivity. Now, when you think of the word radioactive, what do you think of? Most of us would think kaboom, right? You think about this um, explosion, this mushroom cloud of a nuclear bomb, right? So this is exactly the atomic bomb that was dropped on Nagasaki, Japan in 1945. So we think about that, and then we also think about like disasters like the Chernobyl nuclear disaster, or when we think about like even mutants, right, X-Men and stuff like that, how radiation can be dangerous and deadly. In fact, that one was man-made radiation, but there is natural radiation. There is radiation happening all over, all around us all the time. Like gases that are coming from the Earth called radon has radiation. Um, the banana you eat has potassium that is radioactive. In fact, most elements will have an unstable isotope that is indeed radioactive. But all of that radiation is actually not harmful. Okay, and all of that radiation is called background radiation. So the radiation that's just happening all around us. And it turns out all the radiation that we receive in a year, let's say, is 75% of that is considered background radiation. Now, the other type of radiation could also be harmful if you have a lot of it. So the other 25% of radiation that we as normal people receive in a year, it comes from the medical field when you go get X-rays and stuff like that. So it is a little bit more harmful, but you would need again a large amount of it to actually cause harm. But people who work in that field then, because they have to work with it all the time, we need to take precautions to not expose themselves too much of these types of radiation. Okay, so now to talk about radiation, we have to talk about the two types of radiation that the word can mean. And one of them is something we've talked about in the previous lectures here. It's called electromagnetic radiation. And so that's just pure energy. Remember we talked about that? Pure energy in the form of light and waves. Um, and so, and in this radiation, there's a whole spectrum of energy. So on the one end here, we have the radio waves and the microwaves, right? So very long wavelengths, so very weak in energy. On the other hand, we will have radiation that are shorter wavelengths and more energetic. Remember, all light travel at the same speed. So it's all about the wavelengths that correlates with their energy. So on this other end, we have things like ultraviolet, which can be harmful. That's why we try to limit ourselves to the sun because it can cause sunburn or even cause skin cancer, right, from the damage on in your skin cells. And then if we move on further, we can get very, very harmful radiation called X-rays and gamma rays, right? So X-rays, what we just mentioned, what you get at the doctor's office, or gamma rays is just radiation coming from it could also come from naturally too, from cosmic rays. Right? So it turns out this end of the spectrum of the electromagnetic spectrum is very similar to the radiation that we're going to talk about in this video. In this video, we're talking about the radiation that comes from atoms, right? This radiation that is coming from energy, just pure energy, right? But the radiation we're talking about today comes from atoms. But the gamma rays and the X-rays and the radiation that comes from the atoms that we're talking about today share one thing in common. They are very, very harmful because they can be ionizing. So what is ionizing? So when these rays, or when these radiation goes into our body, enters our cells, it can hit a molecule in our cell and dislodge an electron. When you lose a negative electron, you become an ion, right? Hence, it's called ionizing. And these aren't stable. They become very unstable radicals, and so they might splinter off into multiple parts. And for example, DNA can be broken, can be split up. And when you have a messed up DNA, it can mess up your other biochemical processes. They may go haywire. And so when your cells aren't functioning properly, they can develop into to be cancerous, right? When they're not following the blueprint of the DNA. So yes, so ionizing radiation is radiation that is damaging to your cells, to your DNA. So here's an example. In the early days, when they didn't know about the harm of X-rays, for example, this person was the volunteer to expose their hands to the radiation, and after a while, they saw sores and lesions and lots of pain in their hand. Right? But like we said, radiation is harmful, but the background radiation that we receive is actually only 1% of the level of radiation that you need in order for it to cause harm. So the background radiation, you're good. It's only when you work with a lot of radiation, you expose yourself to a lot of radiation, that you should be concerned about it. So to talk about radiation, let's go to the beginning. Let's talk about what is nuclear chemistry. And so in this chemistry, we're basically focusing on what? The nucleus, right? So remember, there's two fields of chemistry. Nuclear chemistry, we don't learn that much in general chemistry. It's a very small topic. Most of chemistry we learn, it involves things outside of the nucleus. So mostly about giving and taking of electrons. So this is a very special topic. In nuclear chemistry, we're only focusing on the center, the nucleus, right? And remember what lives in the nucleus? So this is where you have your neutrons and your protons, right? And they're crammed all in this tiny center here, whereas the electrons are much, much bigger. I heard of statistics once, like, remember, if you imagine a classroom as your atom, right? The nucleus is basically a period that the teacher put on the whiteboard, right? The period is the nucleus. The whole classroom is the whole atom. That's how small the nucleus is. And imagine the nucleus contains the protons and neutrons. So that's all the mass, right? All the mass crammed into one space. That's why the nucleus is extremely, extremely dense. And before Marie Curie and them folks discovered radioactivity, most scientists at the time thought that atoms are quite stable. They don't change. And we kind of know that because from ancient times, the alchemists were trying to change lead into gold, for example, right? That's changing the nucleus, changing the identity of the atom. But they discovered then that not all nuclei are indeed stable. And so when we encounter unstable nucleus, we will see that they will decay. They can't hold together the protons and neutrons, something called the strong force, which is what holds the nucleus together. Sometimes that is very difficult to do, and so we call that nucleus unstable. It will change somehow, and when in that change, it will release particle, and that release is nuclear chemistry. That release is radioactivity. So what are some of the particles that is released, right? So let's talk about the types of nuclear radioactivity. I'm going to talk about four main ones here. Okay, so I'm going to go over this slowly now, but then I'll talk about them in detail in the next in subsequent slides. So the first one is called the alpha particle. Okay, an alpha particle is basically helium nuclei, right? Think about what a helium is. A helium has 2 protons and 2 neutrons, right? But a helium nuclei and then 2 electrons. But a helium nuclei is basically the 2 protons and the 2 neutrons without the electrons. Okay, so that's why we can symbolize the alpha particle as the elements for helium, He. so with a subscript of 2, meaning it has two positive protons, and then a mass number on top of 4, because 2 protons and 2 neutrons together is a mass of 4 AMU. We can also symbolize that with using the Greek alphabet letter for alpha. Okay, the next one is called the beta particle, and the beta particle is basically electrons that is emitted from the nucleus. So electrons usually live on the outside, right, on an electron cloud outside the nucleus. But if something that looks like an electron but is being emitted from the nucleus, we call that a beta particle. Remember, an electron doesn't have mass. That's why the number on top is 0, but it has a charge, right? So it's an opposite of a proton. So the number at the bottom, instead of being 1 as 1 proton, -1 symbolizes that negative charge on the bottom there. And so we also use E for beta particle because, again, it's just basically an electron. Or we can use the Greek alphabet letter beta. Now, the next one is called a positron. And positron is basically the opposite particle of a beta particle. It is a positive electron. Okay, so what does that mean then? So we can also symbolize it with the letter E, but because it is positive, just like a proton is, we have a subscript of +1 in the bottom. But just like an electron, it has 0 mass. Or just like a beta particle, it has 0 mass. Okay, and because it's just like a beta particle, we also use the Greek letter beta for it, but with a +1 as a subscript. And the last radioactivity I want to talk about is gamma ray, and indeed gamma ray is what we've seen in the electromagnetic spectrum. So it is something that can be released in radioactivity, but it's not a particle. It is just pure energy. So we can symbolize that with just the Greek letter there, gamma. Okay, now let's talk about these in detail. The first one is alpha decay. So let's take a look at the model here. When you have a nucleus, we call it the parent nuclei, or the parent nucleus. It is unstable, and then it wants to release particles in order to become a stable nucleus. So if it releases 2 protons, 2 positive charges here, and then 2 neutrons, boom. So it will release those 4 things. We call those 4 things together an alpha particle. The parent isotope is now transformed to what we call a daughter isotope. Now let's take a look at the generic equation there. Remember, you have your parent isotope here. If it releases 2 protons, right, the number in the bottom, Z, has 2 less protons, right? So the daughter is symbolized as Z minus 2. Now the mass number on top, though, because it loses 2 protons and 2 neutrons, together is 4 AMUs, right? So the mass number, you lose 4. So the daughter is A minus 4 from the parent, okay? Now note something here. When you add these, this number below with the number from the alpha particle, it becomes the original, right? So numbers on the top, on the right-hand side together will add up to become the number on the top on the left-hand side. That's a balanced nuclear equation. So let's take a look at an example. You have here uranium-238. It will release an alpha particle to become thorium-234. So how do we do that? How do we know how to do that? So let's go back to our periodic table. And because uranium is way down here somewhere, we're gonna have to zoom in. So let's zoom in into that region down there. Right there is element number 92. Because it's element number 92, when it releases an alpha particle, it releases 2 protons, right? So 92 minus 2 is 90. So you have to go find where element 90 is. And indeed, element 90 is thorium. All right, so that's why this is thorium. So what is the mass, though, that's left over once the alpha particle is released? So 238 minus 4 is 234. So that's why in an alpha decay, uranium-238 will become thorium-234. All right, so let's apply that whole concept again into the next type of radiation called beta decay. Again here, let's take a look at the parent isotope. You have a neutron, and it releases something called a beta particle to become a proton, right? So think about that. What would a neutron release to become a proton? The difference between a neutron and a proton is not in mass, right? They have the same mass, but in charge. So a proton is positive 1, a neutron is 0. So what do you lose to become positive? You would need to lose an electron, right? Think about that. In your life, if you want to become more positive, how do you become more positive? One way is to lose the negativity around you, right? If you cut ties with negative people, you become more positive in your life. Same thing here. So if that neutron gets rid of the negative charge, it becomes a positive charge. 0 minus 1 is plus 1, right? And so therefore it becomes a proton. All right, so I've kind of summarized that here. A neutron kind of transforms into a proton in a process, releases something called a beta particle. So here's an example, thorium-234. When a beta decays, it releases a beta particle alongside with a daughter isotope. Again, notice that 91 plus -1 is 90. 234 plus 0 is 234. They are balanced. So if I were to ask you to predict, let's say I cover this up and ask you to predict what is a daughter isotope, can we do it? And I say it's also a beta decay. So we can, right? Let's go back to our periodic table here. We have thorium there. And we know that beta particles means that you have to basically gain a proton, right? So what's 90 plus 1? 91. So you go to 91, and that's protactinium, so element Pa. So you write Pa and 91 on the bottom. What about the mass number? Remember beta decay, you don't change the number of protons or neutrons, like the total number of that. So the mass shouldn't change. That's why it's 234 mass number there. Okay, so that's beta decay. Now let's go to positron emission. Like I said earlier, positron particles are exactly the same as beta particles, but just the opposite. So the process is also opposite. If beta particle is neutron becoming a proton, releasing a beta particle, then positron emission is when a proton becomes a neutron, releasing a particle called the positron, if you will, of the anti-beta particle. All right, let's think about that again. You have a proton, so positive charge. How do you become neutral? You have a positive proton, you have a positive 1, and you want to become neutral, you lose positive electron. So here we go. We have fluorine 18. It undergoes a positron emission. Again, a positron emission is when you have a proton and it changes itself becoming a neutron. So you release this positron, which is an electron that is positively charged. And so you basically lost a proton, right? Because that proton lost that charge, so therefore it becomes a neutron. So that 9 protons now only have 8 protons left. So you go to your periodic table, what has 8 protons? That's oxygen. So that's why I put an oxygen here. But remember that that proton becomes a neutron. That means your total mass of proton and neutrons doesn't change. That's why your mass number is still 18. Lastly here we have is gamma emission. And so gamma emission, like we said earlier, is pure energy. There's no mass, there's no charge to it. That's why you see both zeros there. And it's just pure energy. So the generic equation is quite simple because the numbers don't change. You just put like an asterisk next to it, and you just put this gamma radiation with 0 mass number and 0 charge at the bottom. Now, even though gamma radiation seems harmless, right? It's not an actual particle, but it's actually the most dangerous. Let's see why. So all these particles can be harmful because they're ionizing, right? And so in order for things to be ionizing, it has to touch your inside of your cells, right? So let's see how far they can travel. If you like ingest all these things, alpha particle is quite dangerous because it is the most massive. But if you just get exposure from outside your body, they have different degrees of harm. For example, alpha particle cannot go through a sheet of paper. That means if you just wear gloves or clothing, you are basically protecting yourself from alpha particle radiation. Now, if you move down this list, the beta particle it's smaller, right? So it's smaller, it can go through more things. So it can go through paper, it can go through your skin. So it can penetrate to you, but it cannot go through metal. Okay, so for example, if you have a sheet of metal, you can't protect yourself from beta radiation. So gamma radiation, even though it has no mass, no charge, whatever, it is most penetrative, right? It can go through paper, it can go through skin, it can even go through metal and concrete. What it can't go through is lead, so you can protect yourself with something very dense like lead. That's why when you go to like the dentist, they put on like a kind of an apron that's pretty heavy before they take an X-ray of you. It's because it's to protect yourself. It's a lead shield to protect yourself from the radiation from the X-ray. Now, speaking of how things can be damaging, radiation doesn't persist all the time, right? Once it undergo radioactive decay, it can't undergo it anymore, right? So that brings us to the next concept here, something called half-life. So let's take a look at this graph here for cobalt-60, and on the y-axis here is the percent, right? So let's say you start out with 100% of radioactive cobalt-60. After a certain amount of time, you would have only half of it left, right? Half of it has decayed, for example, and so you only have half of the radioactive material left. After a certain another amount of time, half of that from 50 will go half to 25 will remain. It turns out that time from going from 100 to 50%, and then from 50% half again to 25% is exactly the same amount of time. And that time is called the half-life. And so for this instance here, for cobalt 60, the half-life is 5.27 years. So it takes about 5 years from 100% to 50%, another 5.27 years from 50% to 25%, another 5.27 years from 25% to 12.5%, and so on and so forth. And so it kind of plateaus because the rate that it decreases it slows down. It turns out every isotope has its own unique half-life. Some could be very, very long, it persists a very, very long time, or some can be very quick, right? For example, uranium-238 has a half-life of 4.5 billion years, right? Whereas, let's say, carbon-14 has a half-life of 5,730 years, right? Much shorter. Now, remember, carbon has multiple isotopes. Another isotope, carbon-16, has a much, much faster half-life. So it's very, very unstable isotope. Is 740 milliseconds as its half-life, right? So it basically doesn't exist in a snap and it's all gone. Let's just do some calculations with this concept. If there are 60 grams of neptunium-240 present, how much neptunium-240 will remain after 4 hours? Okay, so you start with 60 grams. 4 hours later, how much do you have left? Well, it's also given that its half-life is 1 hour. So the first question you should ask yourself is, how many half-lives is in 4 hours? Can you calculate that? It should be 4 half-lives, right? All right, so let's think about that. If you are starting at 60 grams, after 1 half-life, how much do you have left? 60 divided by 2 is 30. And then after the second half-life, divided by 2 again, 15. Third half-life divided by 2 again, 7.5. And lastly, the fourth half-life, because we have 4 half-lives in 4 hours, divide 7.5 by 2 is 3.75 grams. Okay, so that's how you use half-life in calculations. Let's see how we use this in the practical application of it. And it's most practical in something called carbon dating. There's a lot of other kind of ways to date ancient material. Carbon dating is one of them. So here's the premise. Let's give you the premise of carbon dating here. So in the atmosphere, you have these nitrogen atoms, right? And cosmic rays will come down and bombard it and change it into carbon-14 instead. Okay, and there's also other isotopes around. There's carbon-13 and carbon-12. but they are the majority, and there's just a trace amount of carbon-14. But turns out to be our important player here. So in nature, in the atmosphere, there's always this amount, this ratio of a trace amount of carbon-14 to the other isotopes of carbon. Now, remember that carbon is incorporated, is an atom in what important molecule? Carbon dioxide, right? So certain carbon dioxides will have a trace amount of this carbon-14, whereas a majority will have carbon-12, for example. Now the carbon dioxide will be incorporated into plants in photosynthesis, right? And so throughout all plants that are incorporating the carbon-13, incorporating the carbon dioxide into itself, it will have this ratio that is constant in all living organisms. So once that plant dies, though, there is something that is quite different. Once that plant dies, or that cell dies, or that part of the plant is no longer a part of the living part, it's no longer incorporating new carbon dioxide into itself, the ratio will change. And why does the ratio change? Remember that carbon-12 is a stable isotope, so it doesn't decay. So all the carbon-12 you have in that atom will stay a carbon-12 basically forever. But the carbon-14, though, is a radioisotope that is unstable. So it will decay over time. So it will be less and less over time. So if you just measure how much of carbon-14 is left compared to what it should have been at the beginning, then you can know how much time has passed because you have knowledge of the half-life. Okay, and then you can do this also for even animals, because the animals will then eat the plants, so it will also incorporate this ratio of carbons into itself. And then when it dies, we can also carbon date it that way. Okay, so it works for basically all living things, or things that was once living. So let's do the application of that. And so here we have that the fact that carbon-14 has a half-life of 5,730 years. Okay, so in our example, let's say we found this ancient fire pit, and we want to see when did these people start learning how to use charcoal as the fire, for example, because charcoal comes from once living things, right? So we can take a sample of that charcoal and we see how much radiation it's giving off from carbon-14 compared to the ratio of carbon-12 it has. So in this case, it was found that it has 4 counts per minute gram of carbon, okay? But we assume that all living things will have 16 count instead. And therefore, assume that that thing that was once alive has 16 count. So how much time has it passed that it started from 16 and now is only 4? Okay, so think about that. So how many half-lives does it take to go from 16 to 4? 16 divided by 2 is 8, so that's 1 half-life. Divided by 8 divided by 2 is 4, so that's the second half-life, right? So it takes 2 half-lives for it to go down that much. So we then can back calculate, okay, 2 half-lives means 2 times 5,730 gives us 11,460 years. So that tells us that we can date that charcoal to be that old, to be 11,460 years. And so this technique can go up to 50,000 years because there is a limit that it can be useful. Once you go beyond 50,000 years, you have to use other isotopes in nature. Okay, so that's how carbon dating works. What are other uses of radioisotopes, though? So let's go over kind of an overview of some of helpful, beneficial uses for humanity. So oftentimes you can read a lot of ways radioisotopes are used in things in something called tracers. So you add just a tiny amount of it in order to detect things. For example, if you have underground pipes and you have a leak somewhere, you can either dig up the entire pipe system and find the leak, which can be costly, or you can add a trace amount of radioactive material into your water and see where it drips, where it's leaking and dripping, and then where it's concentrating, and then know that area is where the pipe has gone bad, and so you can fix that one area only. And so how we can detect that is we can use something called a Geiger counter. Have you seen this maybe in like sci-fi movies where they're carrying this instrument around and beeps, beep, 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 right? The more it beeps, the more radioactivity is sensing. Yeah, so we can, for example, put iodine 131 into the water source because it's a good radioisotope because it goes away relatively quickly in 8 days, so it doesn't persist in nature and be a harm. But if you see the Geiger counter saying beeping a lot in one area, then you can pinpoint, okay, that's where the leak is, for example. Another example as a tracer is you can try to study how a plant can incorporate nutrients into itself, like different elemental nutrients. For example, if you want to see where phosphorus is uptake, you can feed it with phosphorus 32, which is radioactive, and then you can kind of expose it in almost like a photograph to see where the nutrients goes, for example. Another way you can use radioisotope is in irradiating food, right? So this way, it is used to kill the mold, the bacteria that's on the food. So the ionizing radiation can actually kill living organisms. So you have your food that has maybe bacteria in it, and you can kill it with radiation. Now, does this make your food harmful? Remember that the food is already not growing, right? So even if you damage DNA in your food, it's not going to mutate because it's already stopped its growth process. Because of that, this process is viewed as relatively safe, and it's actually approved by the U.S. By the FDA to make sure your food doesn't go bad that fast. And it is widely used in medical purposes, and there's two ways it can do this. One is called diagnostic, so it can be used to pinpoint if you have a disease or not, or it could be used to monitor that disease in something called like a PET scan, for example. A positron emission is used in this instance. For example, you could use an isotope labeled atom, and you put it onto let's say a sugar molecule. You replace one of the atoms in a sugar molecule with a radioisotope, and then you have the patient kind of be injected with it, and that sugar molecule will be concentrated. For example, if you want to look at cancer cells, because cancer cells love sugar. So if you see all that sugar coming to in a center, then you know that, okay, that center you want to monitor for tumor or cancer. And then, so once it kind of concentrates there, it can emit different light signals, and then you can basically transform that with the computer to make an image of the organ that you're looking at. So that's diagnostic. There's many ways it could be used. But on the other hand, you can also use it as therapeutic, because remember, radiation, it can disrupt and break cells. So if you want to kill specifically cancerous cells, you can irradiate it at that one region to kind of stop the growth of a tumor, for example. Of course, there's side effects of that. That's why people who undergo chemo and radiation therapy have a lot of side effects, because it is quite harmful in terms of not just affecting that region, but other parts that you don't want to affect, like the healthier cells. Okay, so, and then lastly, the positive use of nuclear radiation is, of course, in terms of the energy that we get from it. So let's talk about something called nuclear energy. And there's two types of nuclear energy. The first one is called fission, and they're kind of opposite of each other. One brings nucleus together or atoms together to make a bigger atom. One breaks atoms apart to make smaller atoms. The first one is the breaking apart, called fission. So this is the man-made part of radioactivity. Everything I've talked about earlier is all natural radioactivity. Here is what can be considered man-made radiation. So for example, here you have uranium-236. You bombard it with neutrons. It will become uranium-235, I believe, and then that is unstable. So it then will decompose. It will decay into smaller atoms. One atom is potassium-91, the other one is barium-142, and it releases 3 neutrons. Okay, so that's its nuclear reaction for this fission reaction. And if you add up the masses on both sides, the beginning reactant versus the product at the end, it turns out the masses in general are equal. But if you add it into the masses into as into the smaller decimals of the masses, they actually do not exactly equal each other. So there's a tiny mass discrepancy. And so that tiny mass discrepancy is what gives energy, is what gives us the energy because of Einstein's famous equation E equals mc squared. E here stands for energy. So the energy is equal to mass, m, times the speed of light squared. That's C. Now, remember I said the mass difference is tiny in this reaction, right? But it's being magnified by the speed of light squared. And the speed of light is a very large number. Light travels super fast, right? So because of that small mass discrepancy, you get massive energy. And so notice that I said that if you will bombard uranium-236 with neutrons, you will make this reaction happen, right? But look at this, the product is also neutrons. So that product then becomes a reactant again for the next reaction. So we call that a chain reaction. Okay, so if you have that chain reaction happening all at once, all intensely in a tiny amount of space, releasing so much energy all at once, you get the atomic bomb. So that's what the atomic bomb is. When you split an atom, uranium, so fast, releasing so much energy, it creates a super destructive explosion. But if you were able to control that reaction a little bit more, you can harness that energy instead. And so that's what power plants are. They are the same nuclear reaction, but use one very destructively and one very constructively. This is very attractive, right? Because 1 gram of uranium-236 can give you the same amount of electricity as 3 tons of burning coal, right? And you know that burning coal can cause release a lot of carbon into the atmosphere. Global temperature will change because of that, right? So climate change, whereas uranium, very minimum amount, basically no carbon is being released, so very minimum amount of environmental issues in that respect. Of course, there are other environmental issues like contamination and stuff like that we've seen when there is a nuclear power plant meltdown, for example. Okay, so that's one equation, or that's one reaction that nuclear reaction can undergo. The other one is fusion. Okay, so if we have the one case where one molecule is split, the atom is split to form fission. Fusion is when two atoms come together to form another atom, and in that process, releasing energy. So here we have isotopes of hydrogen. So H3, which is tritium, and H2, which is deuterium. When they combine together, they fuse together, forming helium-4. They also will release energy. And so this fusion reaction is happening constantly, and that's what's giving us life on Earth, because this is the reaction that's fueling the sun. And this reaction requires a lot of energy, so that's why it's happening in the sun. It's a lot of energy burning in order to create this reaction, a lot of hydrogen burning, basically, to release all the energy that's coming down to Earth. And so in terms of man-made, scientists are also working on fusion reactions because it has a much greater potential of harnessing the amount of energy that's coming in from it than fission nuclear chemistry, but they're still working on perfecting this source. All right, so that ends our lecture. Hopefully you have a good overview of what nuclear chemistry is, taking the take-home message that nuclear chemistry is all around us. It can be harmful, but most of it is not in our everyday occurrences is benign, if not beneficial. Yeah. So that ends our lecture. Thank you.